Let's do a couple of example problems for relative motion. The first one is a one-dimensional problem. We have a river, has a steady speed of 0.500 meters per second. A student swims upstream a distance of 1.00 kilometers and swims back to the starting point. If the student can swim at a speed of 1.20 meters per second in still water, how long does the trip take? And then compare this with the time the trip would take if the water were still. We have a fixed reference frame, and we'll talk about the speed of the swimmer with respect to the earth. And then we have the moving water, which is another reference frame, and it's going at a steady speed of 0.500 meters per second. And if I were to just quickly do a sketch here, here's the river, the water is flowing that way. I'm going to let that be the positive direction. So another velocity that we'll have is the velocity of the water with respect to the earth, and we're told that it is 0.500 meters per second, and it's in the positive direction. And then we'll also have the speed of the swimmer with respect to the water. And on the upstream part, that's going to be going in the negative direction. So let's separate this upstream. Okay, we'll have this is going to be minus 1.20 meters per second. And the swimmer is the object of interest, the thing that's moving. We could say the velocity of the swimmer with respect to the earth is going to equal the velocity of the water with respect to the earth plus the velocity of the swimmer with respect to the water. So in this case, it'll be 0.500 meters per second minus 1.20 meters per second, which ends up being, we're down to two significant figures here, just minus 0.70 meters per second for the velocity of the swimmer with respect to the earth going upstream. This is constant velocity, so we can say that if we let this be the positive x direction, we can say that x will equal x naught plus the velocity of the swimmer with respect to the earth times t. If we let x naught equal 0, that's the starting place of the swimmer. Then upstream, we're going 1,000 kilometers, which we can write as 1.00 k, the metric prefix, we can replace with times 10 to the third, and it's meters. So the time, actually this will be negative because it's upstream, and so the time is going to take minus 1.00 times 10 to the third meters divided by that minus 0.70 meters per second. On the way up, we only have two significant figures, 1,400 seconds for the upstream part. Now, going downstream, pretty much everything stays the same except the velocity of the swimmer with respect to the water is positive here. So the velocity of the swimmer with respect to the earth will equal, again, velocity of the water with respect to the earth plus the velocity of the swimmer with respect to the water, and it'll be 0.500 meters per second plus 1.20 meters per second, which is 1.70 meters per second. And then this equation could also work. X will equal x naught plus velocity of the swimmer with respect to the earth times t. In this case, x naught will equal the negative 1,000 meters, and x will be 0. we're swapping places. So we're getting back to the origin. So 0 will equal minus 1.00 times 10 to the third meters plus that 1.70 meters per second times t. Kick that across, divide it by 1.70, and you'll get the time going downstream is 1.00 times 10 to the third meters divided by 1.70 meters per second. And going downstream only takes 588 seconds. So the total time, I should probably label these T sub U and T sub D for upstream and downstream. T sub D plus T sub U, T sub U is going to equal, we have to round, just about 2,000 seconds altogether. And let's see, how many significant figures can we keep on that? We can only keep this to the nearest hundredths place, so we could actually write this as 2.0 times 10 to the third seconds. We're down to 2 sig figs there. The question asks how long this trip would take if the water were still. Well, if the water were still and the student is swimming, that means the velocity of the water with respect to the earth is 0. So the student is basically swimming 2,000 meters at a speed of 1.20 meters per second. So you can convert this into just a distance equals rate times time. The total distance is 2.00 times 10 to the third meters, and that'll equal the velocity of the swimmer with respect to the earth, in this case, times t. T will equal 2.00 times 10 to the third meters, and this time the velocity of the swimmer, or with respect to the water, I guess, but the water's not moving. So anyway, it'll be the 1.20 meters per second. And whatever that turns into, I think it's 1.67. We can keep 3 significant figures on this, times 10 to the third seconds. So it takes less time when there is no current to cover that. Even though coming back downstream, you gain that. But the reason it doesn't just add together is because when we do the calculations, the time ends up being, or the speed ends up being something we divide by. And those different speeds add like weird little fractions. So there's that one. I'm going to skip problem 2. You can take that on as a challenge problem if you want to. It'll test your skills in reasoning and mixes in some free fall motion of a package or kind of projectile motion in a way. So we'll skip that one for now. The science student is riding on a flat car of a train traveling a straight horizontal track at a constant speed of 10 meters per second. Throws a ball into the air along a path that he judges to make an angle of 60 degrees with the horizontal and in line with the track. The student's professor, who is standing on the ground, observes the ball to rise vertically. Okay, we'll have 3 things here, 3 velocities. We'll have the velocity of a ball with respect to the earth. We'll have the velocity of the ball with respect to the student. And then we'll also have the velocity of the student with respect to the earth. This one plus this one will equal this one. So we can just say velocity of the ball with respect to earth will equal the velocity of the ball with respect to the student. Let's let the direction that the train is traveling be positive. In fact, let's let that be the plus I hat direction. Then the velocity of the student with respect to the Earth is just 10 meters per second. He's stuck on the train. The velocity of the ball with respect to the Earth, someone who's standing on the ground sees the ball rise vertically. That means the velocity of the ball with respect to the Earth, I'm going to let up be the positive y directions. Y is up, x is the direction the train's going in, but the velocity of the ball with respect to the Earth, this would be the velocity of the ball the instant it leaves the student's hand, is just going to be v naught y in the j-hat direction. There's going to be a velocity of the ball with respect to the student, and he sees it, or he sees it going up at an angle of 60 degrees with the horizontal, but we'll worry about that in a minute here. I'm just going to say it's going to have some v naught x in the I-hat direction and a v naught y in the j-hat direction. And the direction is such that I'm going to kind of guess that it's going back in that direction, and so v naught x might be 0. There'd be a v naught x and a v naught y and 60.0 degree angle. So v naught y over v naught x is going to be the tangent of 60. All right, well, we'll do our usual thing. The velocity of the ball with respect to the Earth will equal the velocity of the student with respect to the Earth. And this is the instant the ball leaves the student's hand that we're interested in here, plus the velocity of the ball with respect to the student. So there's our equation. And I've got expressions for all of these. Let's figure out what's going on here. Velocity of the ball with respect to the Earth is just some v naught y in the j-hat direction. V naught y in the j-hat direction will equal velocity of the student with respect to the Earth, which is 10.0 meters per second in the I-hat direction, plus the velocity of the ball with respect to the student, which is v naught x in the I-hat direction, plus v naught y in the j-hat direction. Okay, now, the two j-hat terms are going to be equal, and the j-hat terms from one side equal the j-hat terms from the other. The I-hat terms from one side equal the I-hat terms from the other. And if I look at the I-hat terms, there aren't any on the left side, so that means 0 is equal to 10.0 meters per second plus v naught x. Right, setting it up this way, I didn't have to know the sign of v naught x ahead of time. I had an intuitive feel for it, but I didn't have to know it because I find out that v naught x will equal minus 10.0 meters per second. Okay, I kicked that across and then swapped the equation. I tend to do that because I like having this on the left side of the equation. It's just something I do. V naught y, I can solve for that. V naught y will equal v naught x. Actually, in this case, it's the magnitude of v naught x times the tangent of 60.0 degrees. I know that v naught y is not negative, otherwise it wouldn't be above the horizontal. 17.3 meters per second. Well, let's see, now that I know that, the question actually asks, how high above the student's hand does she see the ball rise? How high above the student's hand? We can set up a y equation of motion for projectile motion that looks like y equals y naught plus v naught y t minus 1/2 gt squared. We can say that v sub y will equal v naught y minus gt. One way to solve this would be to take v sub y and set it equal to 0. That's the value at the high point. And then solve for t and plug that into here. We can say y naught is 0 on this. But there's that other equation that v squared minus v naughts y squared will equal minus 2g delta y. Okay, it's one of the versions we saw of this was v2 squared minus v1 squared equals 2a delta x in the x direction. Well, acceleration in this case is minus g, and I'm letting up be positive, so that's why we get a minus sign on the acceleration. So anyway, at the top, v is 0, so I'll have minus v naught y squared equals minus 2g delta y, or delta y will equal, minus divided by minus is positive, v naught y squared over 2g. So my 17.3 meters per second quantity squared over 2 times 9.81 meters per second squared. I get 15.3 meters. This one is a little bit tricky. These are starting to require more thought. Kind of build my solution around this thing and then am careful solving the rest of it.